Harnessing Nonlinearity, Part 1. Phase space, integrability, and chaos. To set the stage for everything that follows, we begin with the foundational language of nonlinear dynamics. And before we dive into the main part of this tutorial, let's take a moment to recall some basic but essential ideas. In nonlinear dynamics, and especially when we study particle motion in accelerators, we use the concepts of phase space and symplecticity to describe how particles move under complex, often nonlinear forces, while still obeying fundamental conservation laws. This naturally brings us to the ideas of integrability and chaos, which tells us when a system's motion can be predicted exactly and how, in reality, most systems live somewhere between perfect order and chaotic behavior. By revisiting these foundations, we'll better prepare to tackle the more advanced concepts that follow. First, let's recall that configuration space is simply the space of all possible positions, the generalized coordinates that describe where a system is at any moment. For a single non-interacting particle, we have three coordinates that can be set in a fixed Cartesian lab frame, or more commonly in accelerator physics, in a comoving Cirefrene frame. Phase space goes one step further. For every coordinate in configuration space, we add its conjugate momentum. This doubles the number of dimensions, but gives us a benefit of capturing the full state of the system at any instant, and allow us to see the evolution of even a many-dimensional system as a single trajectory in phase space. Next, a system is considered integrable if it possesses as many conserved quantities, integrals of motion, as it has degrees of freedom. This is often a consequence of underlying symmetries, as explained by Noether's theorem. These symmetries lead to regular, predictable motion and rule out chaotic behavior in phase space. Integrable systems are important for several reasons. First, they illustrate the deep connection between symmetries and conservation laws, a cornerstone of modern classical physics. Second, they provide exact mathematical solutions, often expressed in terms of regular or special functions that are well defined and thoroughly studied. Third, from a practical perspective, their predictable motion and reduced complexity make them valuable guides for real machine designs. For example, round beam concepts at Web 2000 or the IOTA ring at Fermilab use ideas inspired by integrable models. Finally, and perhaps most overlooked in our field, integrable systems often serve as a simple yet powerful approximations to more complex behavior. Think of Kepler problem, which is not a bad first step toward understanding Earth motion within the solar system. We'll revisit this idea throughout the tutorial and see how, almost mysteriously, the famous Macmillan integrable map is not only an elegant mathematical construct, but also sits as the core of how we can understand conventional multiple magnets. The figures below provide three different examples of integrable systems. From left to right, they show laminar planar flow of an incompressible fluid around the cylinder, a simple pendulum, and an elliptic billiard, where the trajectories of test particles bouncing rigidly off the walls are shown in different colors. Among these three, only the second example, the pendulum, is shown in phase space, where the coordinate x represents angular deviation and y is its conjugate momentum. For the other two systems, only the projection onto configuration space is shown, so x and y are simply represent spatial coordinates. Let's look more closely at the last example, the billiard, which is perhaps less familiar in the accelerator physics community. Since we are using configuration space in this plot, not only do different trajectories intersect with each other, but some even self-intersect. As a result, the system does not obviously appear to be integrable. To see its integrability, we first can examine the phase space of an even simpler system, the circular billiard. At first, it might seem that we need a four-dimensional phase space with two Cartesian coordinates and their conjugate momenta. However, each trajectory can be described by a sequence of points theta and alpha, where theta is the angular coordinate of the collision point along the boundary, and alpha is the angle of incidence. This naturally reformulates the problem in a discrete time setting, since we care only about the moments when the particle hits the wall. Similar to how we use a concept of a one-turn map in accelerators. Clearly, the angle of incidence alpha stays constant, while the angular position theta advances linearly according to alpha. By looking at this phase space diagram, a beginning accelerator student can recognize another parallel with the phase space diagram of a drift space for longitudinal degree of freedom, which is measured in azimuthal angular position along the machine circumference. In integrable systems, the phase space is said to be foliated by invariant curves, or laminas, here parallel lines along theta. The term comes from the ideas of laminar flow, where trajectories do not intersect even in configuration space. The two plots on the right show sample trajectories from this diagram mapped back to configuration space. The top one, in blue, is periodic, often called an N-cycle, while the bottom one in red is quasi-periodic trajectory that never closes. Now that we understand how to visualize the phase space of a planar billiard, let's return to the elliptic billiard, whose phase space is shown below. Once again, the system is integrable, but nonlinear this time. Here we see two qualitatively different types of motion, separated by a separatrix shown in red, and resembling the familiar rotation and libration seen in the simple pendulum. However, it's important to note that not every billiard table shape yields integrable dynamics. On the next slide, we will explore two examples of chaotic billiards. To deepen our understanding, each row here shows the phase space diagram at the center, flanked by two sample trajectories in configuration space. This let us see the distinct signatures that different types of orbits leave in the phase space. In examples A, top left, D, bottom left, and F, bottom right, we see phase space orbits that trace out continuous lines densely filling curves under iteration. These are quasi-periodic orbits. By contrast, orbit C, top right, which illustrates chaotic behavior, fills an area in the phase space, and its configuration trajectory appears more erratic and unpredictable. Also, notice how the configuration space trajectories for the case on the left, A and D, appear to be trapped around 3 or 2 points respectively. This phenomenon is known as mode locking. In phase space, unlike example F, which shows pure rotation, these orbits hops from island to island, forming not just one, but a collection of closed curves. Within each island sits a periodic orbit, 2-cycle or 3-cycle in this case. This situation, where phase space contains a mix of quasi-integrable regions and chaotic zones, is very common and extends far beyond planar billiards. As we've seen through these simple examples, very different systems can share a similar mathematical description. Recognizing this kind of underlying equivalence is central to how we use integrable models to understand and approximate more complex real-world dynamics. For example, the phase spaces shown here has nothing to do with billiards and correspond to the Chirikov standard map, which models longitudinal dynamics in an idealized accelerator with a thin RF station, and the Huanli model from finance, which surprisingly follows similar pattern to the octuple map near the quarter integer resonance. To better understand nonlinear motion in accelerators, we'll now look more closely specifically at the discrete time symplectic dynamics and see how some familiar ideas can be rephrased using the universal language of dynamical system theory. Because the magnets we use in conventional accelerator optics obey Laplace law, the result in dynamics is Hamiltonian, and the transformations that describe how particles evolve in time are symplectic. While continuous time Hamiltonian dynamics is covered in every university curriculum, the discrete time symplectic maps often receive less attention. So before we go further, let's recall some basic definitions and ideas behind symplectic maps. In fact, mappings appear in almost every situation, even when we start with systems that are inherently continuous in time. First, when dealing with systems of ordinary differential equations in higher dimensions, we can introduce a hypersurface sigma, called a Poincare cross-section, which is repeatedly intersected by a trajectory. This transforms continuous motion into a sequence of points, replacing continuous time with a discrete sequence and effectively reducing the dimensionality of the problem. For example, the Huan Li finance model we saw earlier is derived from a system of 3 coupled differential equations and analyzed this way. Second, for non-autonomous systems driven by a periodic force, we can do something similar. Imagine a series of such cross-sections placed along the time axis in the extended space of time plus dynamical variables. This is how the Chirikov standard map is derived from a system of 2 time-dependent equations of motion, and in fact, the familiar one-turn map in accelerators is exactly this kind of mapping, where the position along the machine circumference acts like a periodic driving force. In both cases, the result is a symplectic map of the plane. Throughout this presentation, we will use a dot to denote a time derivative and a prime symbol exclusively to show the application of the map in discrete time, equivalently to writing xn plus 1 equal f of xn. Finally, even when we don't explicitly introduce a surface of section, if we solve differential equations numerically, we must use an integrator. And for Hamiltonian systems, we often choose a symplectic integrator to preserve the underlying structure. Once again, this naturally brings us back to discrete time steps. For mappings of the plane, we are essentially playing a connect the dots game. But instead of following numbers, we follow the mapping equation, and instead of revealing a cartoon character, we recover the phase space diagram. While most of the concepts we will discuss today can, in one or another way, be generalized to higher dimensions, we will focus on systems with 1 degree of freedom and 2-dimensional phase space. In this setting, the definition of symplecticity is especially simple. It's equivalent to the conservation of area and orientation under the map. In other words, the map is area and orientation preserving. Mathematically, this means that the determinant of the Jacobian matrix of the transformation must be equal to 1. For example, the trivial identity transformation or a rotation about the origin both satisfy this condition. Another commonly used linear transformation, reflection with respect to a line, is slightly different. It is anti-area preserving because the determinant of its Jacobian is -1. The 3 images below illustrate these 3 maps applied to an image of a pocket watch showing 9 o'clock. For both the rotation and the reflection, we used an angle of pi/4. Now, let's give a precise definition of an integrable map. A map T in the plane is called integrable if there exists a non-constant real-valued continuous function k, called the integral, which remains invariant under T for any initial condition. For example, a simple rotation has such an integral, and its constant level sets are concentric circles in phase space. On a given invariant circle, we can observe 2 qualitatively different situations. If the rotation angle theta is incommensurate with pi, meaning the ratio is irrational, then repeated iterations will densely trace out the entire invariant curve. In contrast, if theta and pi are commensurate, meaning the ratio is rational number, the iterations will produce a discrete set of points instead. These 2 cases correspond to the familiar examples of quasi-periodic and periodic orbits respectively. The ratio of theta over 2 pi is called the rotation number, or the linear Betatron tune in accelerator physics. In the next tutorial, we will begin by looking more closely at the nonlinear rotation number, and we'll revisit a few more fundamental concepts such as twist and detuning. For those interested in integrability in recent developments, we recommend 2 articles and their references that introduce new automated methods for discovering integrable and near-integrable planar mappings. Along with original articles by Edwin Macmillan and Yuri Suris, they offer a gentle introduction to the challenges involved in identifying integrable discrete time systems. In addition, a companion series that follows explains how to solve integrable maps in the plane, as well as in higher dimensions.